video, we're mainly just using a new vocabulary word called a differential. There's really not a lot new, maybe just a new idea of estimation. So we know that we can make linear approximations. We know that we can write equations of tangent lines where the slope will be the derivative at one given point. We already know how to do that. So some of the formulas you're going to see in your book are just a rearrangement of point slope form. And that's all this is here. It's just if we were to take this guy using our derivative and get y by itself. So the differential is dy, and we've seen dy before inside of dy dx. So this dy, if we look at just that value, that's what we call the differential. So we're used to seeing this as another way to write the derivative. So we've seen dy dx. If I decide to take this guy to the other side, I'm going to multiply it, and I'll get the derivative times dx is equal to the differential. And the differential is just a way to approximate the difference in the y values. Remember, that just means y2 minus y1. And it's just a way to estimate that. So if I ask you to find the differential, differential meaning dy, all you have to do is take the derivative and take that dx to the other side and multiply by dx. We'll need to write our functions in this form when we go to integration, which is our next chapter. Okay? So the big idea in this section is that we're dealing with lots of crazy functions. So the red line is our function, and the blue line is a tangent line. Tangent lines are most often always much simpler because they're linear. They're straight lines. So they're easier to find. They're easier to work with. And if we are at a certain point, A, the values on the red and the blue line are exactly the same. If we look really close to those values, the values are still very close. So you can see if we were to look like, say right here really close to A. If I were to go up to my functions, the blue and the red are still so close. We can use the easier function, which is our linear function, to estimate values on the red function. As we get further and further away from A, like out here, the blue line is no longer a good estimation for the red line's y value. So the closer we are here to my point of tangency, right here in this green box, we can use the tangent line to estimate a value for the actual function, and it's much easier. And so we'll see words like linear approximations or use the tangent line to estimate. There's not a lot new in this section. So our first example says find dy. So find the differential. The way I remember this is I've seen dy dx all year long, and I know that's another way to write the derivative. If I'm just looking for dy, I can take this guy over here by multiplication, and I get that dy is equal to whatever the derivative is times dx. So this is the formula I'm going to use to answer this question. And all that I'm erasing is just kind of how I remember it. So y is equal to x squared, and I need to take its derivative. So the derivative of y is, 2x. And then, so the differential is equal to 2 times x times dx. And it says find this if x equals 1 and dx is equal to 0.01. dx is just an estimation for the change in the x values. So you can see, again, it's not a giant change, so we're really close to that point of tangency. So 2 times 1 times dx, and I'm just multiplying. 2 times 0.01 is 0.02. And so this is an estimate for the change in y. So it's kind of like y2 minus y1, which we also call delta y. Okay? It says compare this value for the actual change in y. For x equals 1 and delta x equals 0.01. So again, the actual change in y we calculate by actually finding those y values and subtracting it. So we need to find them by plugging in our x values. So here I'll have y of 1. That's my first x value. And when I plug it into this function, I get 1. Then if the x values have changed by 0.01, my next y value is 1.01. So again, this is saying I'm starting with 1, and I'm changing that by 0.01 units. And when I plug that in, I get 1.01 to the second power. And you can see our two y values. So the question says find delta y. Again, that means I need to subtract these two y values. And when I do that, I get something really, really close to what I got for delta y. So this is delta y. This is the exact change in y. And dy is the approximate change in y. So you can see they estimate each other. They are very, very close. So this is kind of just proving that as long as we are really, really close to whatever this point of tangency is, and we're really close because we're only 0.01 units away, we can use the differential instead of the actual function. And this is just using the derivative or the tangent line. So find the differentials. We literally take the derivative, so dy dx, and then whatever this dx is, we put it on the side. So the differential is equivalent to 2x times dx. Our next example, again, same deal. I'm going to scoot that over just a bit. So dy dx is equal to, here I have to use product rule. So derivative of x is 1. Bring down your cosine. Add and go back the other way. Derivative of cosine is negative sine. And now I'm going to bring my x down. And to actually find just the differential, I'm going to take my dx all the way over. Notice that's why I put this in parentheses, because the differential is equal to this whole thing times dx. And that's called my differential. And so example 3, this is where you're going to see this on the AP test. It says use the line tangent to the graph. So we need to write an equation for a tangent line, and we write those usually in point slope form. So we need our ordered pair. Our tangent has to be right here at x equals -2. So I need an x and a y. So I want to go ahead and find my y value. So I'm going to get 4 plus 1, or 5. And so my ordered pair, my y value is 5. My slope I'll find here in a second, and x minus -2. And now to find the slope of the tangent line at any given point, we find the derivative, which is just 2x, and we plug in our x value, which in this case is -2. So we get -4. And so this is an equation of the tangent line. And let me draw you a picture just to show what's going on. So you can see, I tried to color code it. I have this red equation in red on the graph. The blue I put in the box here. And so what this is saying is we're drawing a tangent line right here at -2. So that's why I'm using this as my point of tangency. At that point, they both go through -2, 5. So this is 5. This is saying use the red line instead to find this value. And if it asks us to find the value, we would use the blue. So it's again, we're using the red to estimate a value on the blue. And you can see that -2.1 is really, really close to -2. So -2.1 is going to be somewhere like right here. And you can see on our graph, the values are still really, really close. As I move further away, though, you can see this distance gets further apart. So this is like f of x. So this is saying plug -2.01 in right here for x. That will give you the estimated value. So y minus 5 equals -4, and then in this case, -2.01 plus 2. And again, I like this better because I can do this in my head without a calculator. To square that number, I would need a calculator. So here, we probably want to combine like terms first. So we have -4 times -0.01. And when we multiply it, we're going to get 0.04. And on this side, we're going to now add 5. And we see that y equals 5.04 is an estimate for f of -2.01. And we did that without a calculator. And that's it.